All right, good morning, everybody. Welcome to an overcast, sort of rainy or almost rainy Thursday morning lab, Chem 1211, with your host, me, Dr. White. And hopefully you're ready for a fun morning of lab too. All right, here's the game plan. I can go through problem set, answers for 8. We'll do some practice, and then we'll do the lab. And if you have any questions, I'll stick around for a little while after lab to help you out. So, why don't you want to go down? There we go. All right. Well, it seems like a lot of you don't have your webcams on, so you're going to have to use your emoji. Thumbs up, people. Do you see? Let me get to the top here. Chapter 8 calculations on your screen. Thank you. All right. Now, the important thing for these calculations, first of all, read the problem. And the other thing is the relationship of the coefficients in a balanced chemical equation. And let's just do a little review. And make sure I don't make any mistakes like I did the other day, forgetting this too. Now, here we have a balanced chemical equation. And for the balanced chemical equation, the coefficients, the number in front, tell us molar relationships. And this tells us 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. And that's very important because that allows you to make ratios. And when you make a ratio, you can use your good buddy, your good friend, unit analysis. And with that in mind, before I go on, I almost forgot, bad Dr. White. All right, about half hour ago or so, maybe a little longer, I uploaded, those of you who handed it in on time, your lab 6 grades. Because I've been really swamped this week, I apologize. Those who handed in labs late under my amnesty program, guess what? I haven't had a chance to grade them yet. By Saturday morning, I will grade them. I'm hoping later this afternoon I'll have time. Now, with the lab I'm handing back, or I handed back, the most common mistake was where you forgot the problem, which I think I didn't have even a number on the first page at the bottom, add the coefficients. Now, a lot of you just didn't do it. And if you did do it, a lot of you forgot that if there's no number, it's blank in front of the molecule in a balanced chemical equation, the coefficient is 1, and you forgot to add it up. And I'll show you an example. I already got it on the. If I asked you add up all the, and this I'll never ask on a test, but it's good practice. Add up the coefficients for this reaction, 2, and here most of you forgot that that's actually a 1 plus 2 equals 5. And that's the mistake most of you made on the balanced chemical equation lab 6. Now, let me just tell you how I graded lab number 6. If you got 0 wrong, everything was right, you got 10 points. If you got 1 or 2 wrong, 9. 3 or 4 wrong, see, Dr. Wood is really being nice to you. You got an 8. And if you got more than that, I gave you a 7 if you handed it in and got most of them right. And that was one of the main things. And a few of you had problems in terms of balancing a couple of equations. Uh, if you have questions, Monday night, office hour, or Monday after class, even next week, I'll have the answer key for Lab 6. Come and see me after class. All right, let's get back. Now, let's look at the following. Number one, for the following reaction, and I give you a balanced chemical reaction, how many moles of oxygen are needed to make 23.33 moles of carbon dioxide? We have, what are you trying to make or solve for? Moles of oxygen. What are you given? Moles of carbon dioxide, CO2. And here we have that number. That's all we have to work with. What units are we trying to get to? Moles of oxygen. And here, use your good buddy, your good friend, unit analysis. And that's where you, whatever you're trying to get to, you put the units on top of the ratio. Whatever you're trying to get rid of, you put the units underneath. Notice moles of CO2 divided by moles of CO2 give you moles of oxygen, because anything divided by itself is the number one. And where do you get those numbers? You look at the balanced chemical equation. And this tells me I'm looking for a relationship between moles of oxygen, moles of CO2. For every 5 moles of oxygen, I make 3 moles of CO2. For every 5 moles of oxygen, I make 3 moles of CO2. So now I can put it in there. For every 5 moles of oxygen, I make 3 moles of CO2. These are exact numbers. Therefore, this is 4 significant figures. My answer is wrong. Oh no, I made a mistake. That's wrong. It should be 4 significant figures. Oh, there goes my perfect score. So what that means is I have to do that problem. Let's take a look at it. And if we go to our spreadsheet, and the right answer should be 38.88, which is not the right answer I have. Bad, Dr. White. That should be 38.88, not this. And well, I make mistakes too. All right, so the key to this is, where do you begin? Use your good buddy, good friend, unit analysis to set up this ratio, because you know what the answer units you want in your answer. And then where do you get this ratio? From the balanced chemical equation. I'm writing something down. All right, let's have you try one, because Dr. White wants to share the fun. And why don't you try this one? You're given this balanced chemical equation, and as one of your colleagues said last night, my office hour, it's hard to read your handwriting. And guess what? She's right. So let me decode this for you. And that is how many moles of ammonia, NH3, are needed to make 4.58 moles of nitrogen. Your turn. See what a nice person I am? I let you have fun too. I really do have to get a recording of game show music so I could play it for you now. Dun 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 dun. Never mind. Now, normally, if everybody had their web camera on, hint, hint, wink, wink, say no more, I could look around and see if you're done or not. But since some of you are not, give me a thumbs up when you're done. And you can use the emoji. I wonder where they came up with that name. Why don't they just call it a symbole or symbole? That's internet for a symbol. All right, since none of you are giving me thumbs up, let's do it the Zoom way. See, Dr. White is very inventive. I can bet you didn't know I can create new words. I can. All right, I think everybody's done. Let's do this. So the question is, what are we trying to find? How many moles of ammonia? Ammonia is NH3. And what are we given? We're trying to make 4.58 moles of nitrogen. Well, this is the only thing we have to work with. So that's where I'm going to start. What units do I want to get to? Well, we figured that out at the beginning. Moles of ammonia. And now it's time to use your good buddy, your good friend, unit analysis, whatever we're trying to get to. The units go on top of that ratio. Whatever we're trying to get rid of, the units go underneath. And now I'll write those units in. And what I'm looking for is a relationship between moles of ammonia and moles of nitrogen. Where do I get those numbers? From the balanced chemical equation. And this tells me for every 4 moles of ammonia, remember this is 4 moles, I make 2 moles of nitrogen. So the relationship is for every 4 moles of ammonia, I make 2 moles of nitrogen. And therefore, if I notice moles of a nitrogen divided by moles of a nitrogen cancel out, because anything divided by itself equals the number 1, meaning it's gone, and I get the right units. Remember, as I forgot last problem, and so I better make a note. Remember, Dr. White, these are exact numbers. And therefore, this is the only number that will determine the significant figures of my answer, and it's 3. And now I'll take 4.58 times 4 divided by 2. And I'll go to my calculator, even though I probably could do it in my head, but let's not. And I get this, and the number should be 3 significant figures. So the answer is 9.16, which is what I got on the problem set. Wow, I'm on a winning streak or what? But seriously, remember the coefficients are of a balanced chemical equation give you molar relationships. In this one, 4 moles of ammonia, 3 moles of oxygen make 2 moles of nitrogen and 6 moles of water. Now let's go to the real world, and I have never found a balance that does moles. What you do have are balances that do grams. Now here, for the following reaction, propane, that's the C3H8, that's the stuff in the white tanks you use for your barbecue, reacts with oxygen, that's in the air, to give carbon dioxide and water, and what I don't show there, plus heat, which is the flame you use to cook your meat or whatever you're cooking. You can cook vegetables too on a barbecue. Dr. White loves barbecued onions and red peppers. Now I'm getting myself hungry. Stop. All right. There's no, if we look at this problem, how many grams of C3H8 propane are needed to make 24.6 grams of carbon dioxide, CO2, 10 points or something like this. And so I'm trying to find grams of propane. I'm given grams of CO2. There's no way I can go from grams of one substance to grams of another with a balanced chemical equation. Let me say that again in slow motion. There is no way I can go from grams of one compound to grams directly of another using a balanced chemical equation. You need 3 steps. Where do you find those 3 steps? Good news. Thumbs up, people. Do you see number of electrons on your screen? Oh no, aren't you glad I asked? All right, let me scroll. Now, on your screen, do you see mass calculations? Thank you. All right, this is an important information for test number 2, which means you'll be given this. And what do you need to do? Convert the mass, which means grams of A, whatever you're given the grams of, to moles of that compound. That's step 1. Step 2, whatever you just calculated moles of the compound that you were originally given the grams of, you convert that to moles of the product you're trying to get. And finally, since we're trying to get grams, you've now calculated moles of B, you convert moles of that compound to the grams of whatever you're trying to get. So you need 3 steps. And let's take a look at the practice problem. Now, for this one, we're trying to get grams of propane, and we're given grams of carbon dioxide. First step, we go from grams of CO2 to moles of CO2. Again, first step, grams to moles of whatever you're given. So I have these grams. I want to go to these moles. How do I do that? Well, I use my good buddy unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. I should ask, anybody having nightmares where I'm saying, use your good buddy, your good friend, unit analysis, whatever goes on top? I hope not. That would scare me too. Hopefully you all have sweet dreams. All right, so whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. Where do I get a relationship between moles of CO2 and grams of CO2? Well, good news. You look at important information, and it says right here, 1 mole of a compound equals the molecular weight of that compound in grams. 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of that compound is the sum of all atomic weights. Remember, molecular weight is the sum of all atomic weights. So therefore, if I go back to my problem, all right, Zoom is playing games with you. Everybody see problem 3 on their screen? Thank you. All right, now, where do I get this? 1 mole equals the molecular weight. What's the molecular weight? 2 carbons is 1 times 12. Oxygen is 16. 2 times 16, 32. You add it up, you get the same number of significant figures to the right of the decimal as the number with the fewest significant figures. They're both 1. So the answer is 44.0. You do the math, 3 significant figure, 1 is an exact number, 44.0 is 3 significant, and is the answer you get. Now, on these multi-step problems like this one, you can round off at each step, which Dr. White does, or wait until the end. And what I will always do is calculate both, and on a test, both answers will, if they're different, will always be correct, because I'm not going to force you to do what I do, which is round off at each step, not the very end. But I know chemists who do at the very end. So, all right, now we have moles of CO2, but we're trying to get the grams of propane, C3H8. Second step, moles of CO2 to moles of the answer we're trying to get to, which is moles of propane, C3H10. Whatever we're trying to get to goes on top of this ratio, moles of C3H8. Whatever we're trying to get rid of goes underneath, moles of CO2. Where do we get those numbers? From the balanced chemical equation. 1 mole of propane makes 3 moles of CO2. 1 mole, when there's no number, it's the number 1 in front of the coefficient. 1 mole of propane makes 3 moles. These are exact number, 3 significant, 3 significant. And now I have moles of propane, moles of B. And now, sorry, this thing keeps on popping up on there. Go away. And now step 3, I have moles of propane, C3H8. I want to go to grams of propane. I use unit analysis, grams goes on top, moles of propane, C3 goes underneath. Where do I get that? You look at the important information, test number 1, and you use the 1 mole of a compound equals its molecular weight, and the very lowest bottom, if I put my cursor there, that pop-up stupidity will show up. So I'm not going to do it. We have 3 carbons, 8 hydrogens. Remember to use 3 significant figures for all atomic masses. You add it up, do the proper significant figures for addition, and the molecular weight of propane to 3 significant figures, or to the proper significant figures past the decimal, is 44.1. Do the math. And if you round off at each step, you get 8.18 grams of propane. Or if you see underneath, you round off at the end, you get 8.20. And that's how you do it. All right, let me have you have some fun. All right, let's look at this problem, and I'm going to have you have a chance to do it. And the question is, how many grams of hydrogen gas, H2, are needed to make 125.6 grams of HCl? Now, to help you out, and you'll get this on the test, you won't get this, but here's a little help. And step 1, step 2, and step 3. And that's my little help for you. And it's your turn. Have fun. Ooh, I forgot something important. There. Good news, I'm not going to do my game show music singing. I don't want to ruin your day. Probably already did already. And no, I won't start singing 100 bottles of beer on the wall. For those who don't know that song, look it up on Google. I'm sure everything's available to find information like that via Google. Oops. Oh, thank you, Gabriella. But jazz, think about it. It gets burned into your brain so you can use it. Oh, by the way, I'm going to have to charge you extra for having your roommate watch me now. What's your credit card number? No, I'm just kidding. Oh no, people don't want to use the polling. I've got a revolt on my hands. Oh no. Oh no, Samar. I'm going to do it the old fashioned way. All right. Thumbs up if you're done. Thumbs down. Oh, you can't do thumbs down in Zoom. I wish they did. I'll have to write them so they can add that new symbole. For those of you who finished early, please wait. I think I said symbole, not imbole or imbole. What would be an imbole? Get mad at someone and say, boy, you're a real imbo. Make up new words, confuse people. Nah. All right, I'll give you another minute. Go. And I'm watching the clock now. All right, let's get going. All right, so how do you proceed? You need 3 steps. And first of all, what are you being asked to find? Grams of hydrogen. What are you given? 125.6 grams of HCl. And you need 3 steps, which conveniently somebody wrote right up here. And the first step, whenever you have in grams, you go to moles, and you know 1 mole of a compound equals its molecular weight in grams, and then moles to moles, A to B, and then moles of B to grams of B. And here we go. We have the grams of HCl. We want to get the moles of HCl. We use your good buddy, your good friend, unit analysis, to put that on top. The moles go on top. That's the answer I want to get to. The answer I want to get rid of is grams of HCl, so I'll put that underneath. Where do I get these units? 1 mole of a compound equals its molecular weight in grams, and the molecular weight, which I have over here, is the sum of all atomic weights. And when you add it up using proper significant figures for addition, you get 36.5. 4 significant, 3 exact number, 3 significant figures. Now, second step, whatever I found moles of, in this case HCl, I want to go to moles of my answer, hydrogen. So start with the moles of HCl. I want to go to moles of hydrogen, use unit analysis again, your good buddy, your good friend, and moles of hydrogen go on top, moles of HCl go underneath. Where do I get these numbers? From the balanced chemical equation. For every 1 mole of hydrogen, I make 2 moles of HCl. Remember, the coefficients are balanced of a balanced chemical equation are molar ratios. So for every, when there's no number, it's number 1. For every 1 mole of hydrogen, I make 2 moles of hydrochloric acid, HCl. And now, I remember these are exact numbers and they don't play a role in my significant figures. This is 3. My answer should be 3. Moles of HCl divided by moles cancel out. I'm left with moles of hydrogen. And now in step 2, I now have 1.72 moles of hydrogen. Now, what do? Well, I'm trying to get the grams of hydrogen. I have moles of hydrogen. I do step 3. Moles of B, in this case hydrogen, the grams of B. And here I take whatever units I'm trying to get to. That's what my good buddy, my good friend unit analysis tells me to do. And I put it on top of the ratio. Whatever I'm trying to get rid of, I'll put underneath the ratio. And where do I get these numbers? 1 mole of a compound equals its molecular weight. 2 hydrogens, 2 times 1.01. Remember, using all atomic weights to 3 significant figures. That'd be 202. This is the exact number, 3 significant figures. Now, the 3.47, if you round off at each step, if you round off at the end, you get 3.48. I'd highly recommend you practice these. I'm stealing this from Monty Python, one of my favorite all-time TV shows. If you've never seen Monty Python and the Flying Circus, you're missing something totally funny. And it's on YouTube, some of their skits. And hint, hint, wink, wink, say no more. You should know how to do that problem. Practice it. Now, one of the things I noticed, oh no, I didn't put any practice problems for limiting reactants. So I'm going to write some over the weekend or probably Friday afternoon. I'll send out an email and Monday I'll go through some, but guess what? I can create one or two right now, and I will. All right, 5 points. Here's a balanced chemical equation. If you react 7.61 moles of ammonia with 6.01 moles of oxygen, then how many moles of nitrogen will you make? So what are we being asked to find? Moles of nitrogen. What are we given? 7.61 moles of ammonia and 6.01 moles of oxygen. And how do you do this? You look at important information, test number 2, and you see limiting reactants. Determine the number of moles of product produced using the moles of each reactant. The lower number is the answer. So what we have to do is 2 calculations for each reactant, find out how many moles of the product we will make, and the lower number is our answer. So, Dr. White, get the word. Oops. So, let's look at this one right here. I want to go from 7.61 moles of ammonia to moles of my product, what we're trying to find. I'll use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. Let me get this back down here. There we go. And I'm trying to get the moles of ammonia. And where do I get the numbers here? From my balanced chemical equation. For every 4 moles of ammonia, I make 2 moles of nitrogen. For every 4 moles of ammonia, I make 2 moles of nitrogen. This cancels out. I'm left with the right units. And now I can first copy down so I don't forget their numbers. I can go to my calculator, which I will now. And to 3 significant figures, that's 3.81 moles. So we're going to get 3.81. Now for the other one, I'll use moles of oxygen. I want to get, again, 2 moles of nitrogen. And so I don't cheat you on this Thursday. It's time to use your good buddy, your good friend, unit analysis. I won't even charge you for that extra. All right. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And where do I get these numbers? From the balanced chemical equation. For every 3 moles of oxygen, I make 2 moles of nitrogen. For every 3 moles of oxygen, I make 2 moles of nitrogen. Notice moles divided by moles of oxygen cancel out. I'm left with the units I want. And I'll now go to my calculator. And this is the number I get, and that to 3 significant figures would be 4.01. And when you do this, the lower answer of these two is your answer, and there's my answer. The answer is 3.81 moles of nitrogen. And if I look at the clock, oh, did I time it right or did I time it right? It's time for Dr. White's stretch and for you to take a break. I'll see you at 9:55, 5 minutes from now. Bye. I gotta get you all back to work. Time to start. I bet you never thought taking chemistry you'd hear all those special sound effects. All right, let me have you try one of the limiting reactant problems. And it's time for you to try one too. How many moles, oops, how many moles of, that sort of fell off. Oh no, I got hit by the dreaded many of removal virus. How many moles of, how many moles water are made if you react 2.00 moles of hydrogen with 4.00 moles of oxygen? And just to remind you, let me show you something first. Important information, limiting reactants. Determine the number of moles of each product used using the moles of the reactant, or moles of the number of product made, produced using the moles of each reactant, and the lower number is the answer. So you have to determine the number of moles of the product using each reactant, and the lower number is the answer. And let me get you back to here. Your turn. All right, let's try the polling once more. Oh, and the votes are coming in. All right, I think everybody's done. Let me give you another 12.6 seconds. Go. All right, let's do it. So what are we trying to find? That's the first question you should be able to answer. And that's moles of water. What are we given? 2.00 moles, not mil, moles of hydrogen and 4.00 moles of oxygen. I hope I didn't make a big mistake. No, I don't think so. All right. And I might have. So you need two steps or two calcs. And the lower one is the answer. So I'll start with 2.00 moles of hydrogen. I want to get to moles of water. Whatever I'm trying to get to, when you use your good buddy, your good friend, unit analysis, that's the wrong color, bad Dr. White. Whatever you're trying to get to goes on top of this ratio. Whatever you're trying to get rid of goes underneath. Where do I get these numbers? The ratio of moles of water to moles of hydrogen from the balanced chemical equation. For every 2 moles of hydrogen, I make 2 moles of water. So I can put this here, and this is 2.00. And that's my first calculation. My second one, I have 4.00 moles of oxygen. And I want to find out how many moles of water I'll make. And once again, I'll use my good buddy, my good friend, hopefully yours too, unit analysis. Whatever I'm trying to get to, the units go on top of the ratio. Whatever I'm trying to get rid of, the units go underneath. And where do I get a ratio of moles of oxygen to moles of water? From the balanced chemical equation. For every 1 mole of oxygen, I make 2 moles of water. And remember, all these are always exact numbers. So if I do the math, I get 8.00. And the answer is the lower one of those two calculations. So my answer is 2.00 moles of water. And that's how you do it. And good news, I've covered everything we're going to have on test number 2 next week. So this way you have plenty of time to go back and study some more between now and next Wednesday, so you'll do good on test number 2. Now, make sure you do all the practice problems again at least once. I'm going to say that again. Don't tell anybody and give any secrets away. Do the practice problems. And you can also look at the videos and see this international video star, YouTube star, me, Dr. White. All right, any questions before we go into our lab? All right, well, in that case, it's lab time. And today I have some show and tell for you. Oh, that reminds me. When I was in grade school, we had show and tell. The teachers I had were very afraid of what Dr. White would bring in because most of it was science that they had no idea what was going on. In fact, I just remembered back in, what was it, 7th grade in English, we were supposed to do a paper on whatever we want, a real official paper. So I did one on plain polarized light, and the teacher had no idea what I was talking about. It was a good paper. She did not like me because I would do things. She was not a science person, which is okay. But, anyways, let's think about something. Got a bottle here with a liquid in there. How do I know how pure it is? Is it one substance or more than one substance? Or if I have other things, and it's time for show and tell. Food coloring. I think you're all familiar with it. And they come in, oh, isn't this cute? The little cute little thing. I'm not going to open it up because the stain's real good. But food coloring. See the liquid in there? I don't know. Can everybody see the liquid in there? Yep, you can. Hopefully you can. Is that one substance or is it a mixture of substances? How do you find out? Well, it turns out chemists, isn't that cute still? Plus, it's my favorite color, red. Uh, anyways, how do you know if something's pure or not? And that's an important question. And how you do that is by analyzing it with a technique called chromatography. Now, there are different types of chromatography. How many of you have ever seen the CSI shows, which I don't watch because I can't buy into stuff that's pseudoscience? I just can't. Most, have you seen where they inject something into a machine or have an automatic injector? And after a while, they see the CRT, the computer screen with these lines on it, and it tells them, ooh, that's that compound, this and this, and that sample from that, what you pick, whatever heinous crime you like to put in there, so we can go catch the evil person. Well, what that is a form of chromatography, separating different components of a mixture and identifying them. Now, the one they're using is called gas chromatography, which Dr. White used in grad school and also in industry. In fact, come to think of it, I hadn't thought of it. Oh, when you defend your thesis, it's called defense of your thesis. You're there with your research advisor and three other professors, and it's a whole formal thing, and you defend your thesis. They ask you all questions and everything. It goes on for a couple hours. And near the end, at least at Michigan State, they have a part of your defense, which you're told you're going to get this, where they can ask you anything about anything in your area of chemistry. And one of the professors asked me, can you on the whiteboard, we were in a small conference room, please show all the parts of a gas chromatography and explain how it works. Well, luckily, Dr. Whitehead in my research group, I was responsible for a couple of years keeping them working, so I knew how to take one apart and put it back together. But before all that electronic equipment, how did they do that? Chemists found that by putting a sample on a piece of paper, it's called paper chromatography because you use paper, and by having a liquid go up the paper, absorb on there. How many of you ever seen a paper towel get wet and the liquid goes throughout the paper towel? And depending on what liquids, and that's called the elution liquid, you can separate mixtures on a piece of paper. And if they're colored, you can see the different ones. So today's lab deals with paper chromatography. And as you notice, I say, how do you determine if a substance is pure or mixture? Use chromatography. Now, the original term, I believe, and don't quote me on this, but I think chrome means color, graphy means make a graph of it. And chromatography is an analytical method. By the way, most of the, like all the chemists you see in CSI or the technicians who analyze things, those are all analytical chemists, which is an important branch of chemistry. I'm an organic chemist, but I've used analytical chemistry throughout my career, things that others have developed or I have. All right, and this allows you to separate it. There are different types, and the oldest one is paper chromatography. Let's take a look at YouTube, not YouTube, Wikipedia. And thumbs up, people. Do you see the pretty picture on your screen? Thank you. Now, what this shows you right here, you have a solvent, your eluting solvent, and the liquid goes up the paper. And when it goes up the paper, due to different intermolecular forces, inter meaning how they interact, the molecules with the solvent molecules, will cause different compounds to travel up the paper at different rates. And that's a way of being able to identify. If you only see one dot, it's pure. If you see like here, a lot of dots, it's a mixture of three things. And that's paper chromatography. Now, when we do this at COD, it's not as fancy as this one. Oh no. Gabriella, can you see the picture? Hold on. No, you can't. All right, now can you see it? All right, let's start again. Paper chromatography. I hate Zoom when it plays tricks like that on me, because on my screen it says you should be able to see it, which is why I came up with the thumbs up people. Thanks to all my thumbs up people and others who gave me information. All right, let's do this again. Here's a piece of paper. You put a dot right around here above the solvent, and the solvent goes up the piece of paper where it ends. You never let it go all the way to the top. Is called the solvent front, and it separates these into different dots. Now, there's a measurement from where you put the material to where the different dots are. That's called the RF value, which you're not going to do in this lab. But in case somebody comes up to you and taps you on the shoulder, say, do you know where RF value comes from? You can say, yes, paper chromatography. Now, there's another form of chromatography similar to this, where instead of using a paper, you use silica gel on a microscope slide. It's the same thing, except the paper, this is a slide. And Dr. White did a lot of those in grad school. And in fact, every Monday morning, I used to make up about 100 of them because they were expensive to buy, but cheap to make yourself. And you learn from I did from other grad students, how to make your own microscope chromatography slides. We didn't do that much paper chromatography because for what I was working with, the slides were better, but the principle is the same. So in paper chromatography, you put the paper in a beaker with a small amount of solvent, or you can use mixtures, and it's slowly absorbed and moves up. That's called the solvent front. And different compounds move at different rates or different distances on the paper. And that's how you can tell if you have a mixture and it's separated into different compounds. And if it's colored, you can do that. If you only see one spot, then it's a pure substance. If there's more than one spot, that will indicate how many different substances. Now, the RF value, and I forgot what RF stands for. I'll have to look it up again. I've been using it so many decades, you forget what it means. Something factor, I can't remember what the R is. But anyways, is the value showing the numerical form of different substances on a paper. And you can see, if you want to learn about RF factor, go to Wikipedia and learn about it. Now, if we were doing this in a lab, if you were actually in a lab, you'd cut the paper from filter paper, use a pencil, not a pen, because ink has different substances where lead is inorganic and it won't. You draw a line about a ½ inch up the strip. And if you were in a lab, because we're working with food coloring, which stains your skin, you put different dots with a toothpick, or there's a thing called a melting point tube, or just a hollow tube uh, that you can put it on there. And then you put some water and you put it in there, and the level of the water should never uh, be below the line on your paper. Then you cover it with aluminum foil or plastic wrap. I think we use plastic wrap. And you wait about 6, 7 minutes. And then when it's about a half inch, you take it out and you observe it. If there's more than one dot, one or more dots, record that in the table. And then you clean up. Well, you don't have to do that. Now, here's the different food colorings you'll be using today: red, green, blue, and yellow. And here you've got to put the number of spots, which otherwise known as the numbered dots or spots in the video. Where's the video? Well, I'm going to show you that. By the way, in that video, the top sample is red, next one is green, next one is blue, then yellow, and the very bottom one, which we're not doing, is black. Let's look at the video. Quick question. Do you see YouTube on your screen? Thank you. And here are your dots. This is at a right angle, but here's your red. And each number you see on the screen corresponds to a dot, what I would call a dot. And you wait until it goes up to a certain distance, then you stop it, take it out. Oh no. Hold on a second, I gotta move something out of my way. All right, let's stop it right here. And see the numbers right here? That corresponds to what I call a dot. And see the point right here? That's where you originally put your compound or whatever substance or mixture, the food coloring. And if you see more than one number, that means there's more than one dot. And after watching the video, the very top one is red, and you're to put in how many numbers or dots do you see, and do that for each of the food colors. And then answer the questions. Notice I say how many spots. Last semester, students got confused with that because they didn't see just a little dot. And spots are anything with a number is a spot. Let me give you go back to the video. Everybody see it on your screen? See where it says E124? That's one dot. E122 is another dot. So this sample would have two dots. Everybody should get red has two dots, correct, in your data. And that's how you do it. And that's today's lab. And remember, if you were in the lab, we do this with the, aren't they cute? But anyways, these little, the food coloring. Oh, one thing I should tell you, don't tell anybody, when you do it in the lab, because COD uses cheap filter paper, it doesn't look as pretty as on the video. It looks, and I have people look at the video, even if we're in the lab, because it goes, it's not pretty. Anyways, that's today's lab. That's today's fun together. I hope you enjoyed having a fun morning of chemistry and lab with Dr. White. If you have any questions or need any help, I'm going to stick around for a while. And I'll help you. And with that, I'm going to do my world famous goodbye. Gehen gesund. Goodbye. Remember, study for test number 2. That's next Wednesday. And I'll see you on Monday.